Hi everyone, myself Dr. Ashok Babu, working as Professor and Head EC Department. So in this video, I am going to discuss about the reflection coefficient and standing wave ratio of a transmission line. So here the reflection can be defined as the reflection of an energy occurs when there is an impedance irregularity. When there is some impedance irregularity, then we can have the reflection. That is, when the primary constants of the transmission line are not uniform along the line, then we may have the reflection in a transmission line. So here the phenomena of setting up a reflected wave at the load due to improper termination or due to impedance irregularity in a line is called reflection. I repeat the definition. The phenomenon of setting up a reflected wave at the load due to improper termination or due to impedance irregularity in a line is called reflection. The reflection will be maximum when the line is open or short circuited. So and will be zero when ZR equal to Z0. When ZR equal to Z0, the reflection is zero, and the reflection is maximum when it is open or short circuited. So reflection coefficient is defined as the ratio of reflected voltage to the incident voltage. It is VR by VI. The reflection coefficient can also be defined as in terms of the ratio of reflected current to the incident current. So it means IR by IA. So here it is denoted as K. The reflection coefficient can be defined as denoted as K. Let VI and VR be the incident and reflected voltages respectively. Then we can define K, reflection coefficient K is equal to VR by VI. Similarly, IA and IR be the incident and reflected currents respectively. Then we can define the IR by IA is equal to minus K. So in terms of voltage, it is K. In terms of current, it is minus K. So reflection coefficient is a measure of the voltage. Reflection coefficient, next one. So it is about the reflection. Now we can define the reflection coefficient as reflection coefficient is a measure of voltage and current reflected from any point in a transmission line due to impedance irregularity or from the receiving end due to improper termination. So in two ways we can define the reflection coefficient. Reflection coefficient is a measure of the voltage and current reflected from any point in a transmission line due to an impedance irregularity or from the receiving end due to improper termination. We can have the reflection. So due to reflection we can find out the reflection coefficient. So here the fundamental equations for voltage and current at any point of a transmission line are, we can define the two transmission line equations are the voltage equation and current equation. These two are V is equal to B into e power minus Px plus A into e power Px, and current equation is I is equal to B by Z0 into e power minus Px minus A by Z0 into e power Px, where A and B are the small a and small b are the some constants and P is the propagation constant. So here if Y is the distance measured from the termination ZR, Y is the distance measured from the termination ZR, the above equations can be expressed in terms of Y as by simply replacing x equal to minus Y. So if you substitute x equal to minus Y, then we can convert the equations in terms of Y, and where Y is the distance measured from the receiving end. X is the distance measured from the sending end, where Y is the distance measured from the receiving end. Therefore, the voltage and the current equations are V is equal to, in place of B, in place of minus X, here I am substituting Y. In place of X, I am substituting minus Y. Therefore, the voltage equation becomes V is equal to B into e power Py plus A into e power minus Py. And the current equation is I is equal to B by Z0 into e power Py minus A by Z0 into e power minus Py. So the first term in equation 4 represents the incident voltage Vi, while the second term represents the reflected voltage Vr. So because incident voltage must go increasing and reflected voltage generally decreasing as Y increases. So here we can observe that the first one is B into e power Py is the incident wave, second one is a reflected wave. First one is incident wave and second one is a reflected wave. Similarly, so in current also first one is the incident wave, second one is the reflected wave. So at the termination ZR, where ZR is the receiving end impedance, at the termination because y is measured from the termination. Let us assume y is equal to 0. So where from the receiving end, we can assume V is equal to VR and I is equal to IR, where VR is a receiving end voltage, IR is a receiving end current. Then if you substitute these two in above equation and transmission line equation, so we can have VR is equal to B plus A. VR is equal to B plus A, because what is the equation here? Here we have V is equal to B into e power Py plus A into e power minus Py. So if you substitute y is equal to 0, V is equal to have B into e power 0 plus A into e power 0. Therefore, e power 0 is 1, e power 0 is 1. We have V is equal to A plus B. Similarly, in current equation also, it is I is equal to B by Z naught into e power 0 minus A by Z naught into e power 0. For I is equal to, we can write B by Z naught minus A by Z naught. For B minus A by Z naught, we have I is equal to B minus A by Z naught. So there are the two equations. IR is equal to B minus A by Z naught, or we can write IR into Z naught equal to B minus A. So here if you solve these two equations, we can find the B and A and B constants. So from these two, if we add these two equations, that is A plus B is equal to VR, and here we have B minus A. B minus A is equal to, we have IR into Z naught. So if we add the two equations, I cancel each other. We have 2B is equal to VR plus IR into Z naught, or B is equal to VR plus IR Z naught by 2. So in a similar fashion, we can find out the A value also. So here B is equal to VR plus IR Z naught by 2. Similarly, we can find out the A value. The way A value is A equal to VR minus IR Z naught by 2. So the voltage reflection coefficient can be defined as, here the voltage reflection coefficient is equal to K, which is equal to VR by VI, reflected voltage by incident voltage. So here the reflected voltage is A into e power minus Py by incident voltage is B into e power Py. Therefore A by B into, so if we move the e power Py to the numerator, A by B into e power minus 2 Py. So at the termination ZR, we can assume that Y is equal to 0, because Y is measured from the receiving end. Therefore, here if you substitute Y is equal to 0 in above equation, the reflection coefficient K is equal to, it is A by B into e power 0. Therefore, the reflection coefficient K is equal to, we have A by B. And from the equation, from this equation 5, here we can find out the K value. K value is, so here A by B. K value is A by B, where A is, K is equal to, it is VR minus IR Z naught by 2 by VR plus IR Z naught by 2. 2 cancel each other. Therefore, we have K is equal to VR minus IR Z naught by VR plus IR Z naught. Then you can simplify the equation again. So divide the numerator and denominator by IR. So here if you divide the numerator and denominator by IR, then the equation can be modified as, and we can substitute ZR equal to VR by IR. Then the equation can be modified as, it is VR by IR minus Z naught by VR by IR plus Z naught. Then if you substitute VR by IR equal to ZR, we can have the ZR minus Z naught by ZR plus Z naught. So here we have the different load conditions. Three load conditions are, the first one is a match load condition. The match load condition means ZR equal to Z naught. And second one is short circuited load, and third one is open circuited load. First one is match load. For match load, if we substitute ZR equal to Z naught in the above equation or in equation 6, therefore K is equal to ZR minus Z naught equal to 0. Therefore the equation becomes K equal to 0. So if there is a match load, then the reflection coefficient K equal to 0. Then second one is for short circuited. For short circuited end, we can substitute ZR equal to 0. So here if you substitute ZR equal to 0, then we can have K is equal to minus Z naught by Z naught. Z naught cancel each other. Then we have minus 1. Then if we open circuit the transmission line, then we can substitute ZR equal to infinity. Then we have K is equal to, here if we take ZR common, ZR into 1 minus Z0 by, so in denominator also ZR, if we take common, 1 plus Z0 by ZR, 1 plus Z0 by ZR. So ZR cancel each other. If you substitute ZR equal to infinity, that is K is equal to 1 minus 0 by 1 minus 0, that is K is equal to 1. K is equal to 1. So in this way we can find the reflection coefficient for matched load, short circuit load and open circuit load. Then here, so there are the three conditions to find the reflection coefficient. Now we will define the standing wave ratio. So to define the standing wave ratio, so here you assume the waveform. So here the thick line is the voltage one and dotted line is the current. So here we have voltage maxima is there, voltage minima is there, and current maxima is there, current minima is there. So it is the current maxima position, current minima position, and voltage maxima position and voltage minima position. So here the distance, you can observe the distance between current maxima and voltage maxima is lambda by 4. The current maxima and voltage maxima is lambda by 4, and the distance between two voltage maxima, is lambda by 2. Similarly, the distance between two current maxima is also lambda by 2. The distance between two current maxima is also lambda by 2 only. Next, standing wave ratio. So here the reflection takes place. The reflection takes place when line is not terminated in the characteristic impedance. So if there is improper termination, then we can have the reflection in the circuit. So this causes the reflection of waves. The combination of reflection and incident wave give rise to a standing wave. So using the standing wave, we cannot transfer the information. So using the traveling wave only, we can transfer the information. So when the reflection takes place in a transmission line, at some points, the incident and reflected signals are in phase, and both the components add together. At some other points, the two components may oppose each other. So here the points where the resultant signal is maximum is known as voltage or current maxima. The points where the resultant signal is minimum is known as voltage or current minimum. So here we can define the voltage maximum and the voltage minimum, current maximum and current minimum. So here the voltage maximum equal to, it is VI plus VR, where VI is the incident voltage, VR is a reflected voltage. V minimum is equal to VI minus VR. Similarly, I max equal to II plus IR, and I minimum is equal to II minus IR. So the ratio of maximum and minimum magnitude of current or voltage on a line having standing wave is called the standing wave ratio and is normally abbreviated as SWR, and it is denoted as S. So I repeat the definition: the ratio of maximum and minimum voltage, minimum magnitude of the ratio of maximum and minimum magnitude of current or voltage on a line having standing wave is called the standing wave ratio, and is normally it is denoted as SWR. Here SWR is of different types. So here we can define the voltage standing wave ratio and current standing wave ratio. So here the voltage standing wave ratio VSWR equal to, it is V maximum by V minimum, where V max is nothing but 1 plus mod K by 1 minus mod K. Our current standing wave ratio is 1 minus mod K by 1 plus mod K. So here VSWR is always greater than 1, and when it is equal to 1, the line is correctly terminated and there is no reflection. So here we can find out the VSWR as VSWR equal to, it is denoted as S equal to V max by V minimum, and which is equal to V max can be defined as VI plus VR. V minimum can be defined as VI minus VR. Therefore, VSWR equal to, if you take VI common, 1 plus VR by VI by 1 minus VR by VI. But VR by VI is known as a reflection constant K. Therefore, we can define the 1 plus K by 1 minus K, where K is equal to the ratio of reflected voltage to the incident voltage. So it is a reflection coefficient. So here we can define the S as VSWR is denoted as S. Therefore, S equal to 1 plus mod K by 1 minus mod K. 1 plus mod K by 1 minus mod K. So if we cross multiply the equation, it is S minus S into mod K, which is equal to 1 plus mod K. 1 plus mod K. Therefore, it is S minus 1 is equal to, it is S into mod K plus mod k. So here if you take common of mod k, it is s plus 1. Therefore, k is equal to, or mod k is equal to, it is s minus 1 by s plus 1. S minus 1 by s plus 1. The reflection is a relation between reflection coefficient and VSWR, where k is a reflection coefficient, s is a VSWR. So it can be related as k is equal to s minus 1 by s plus 1. K is equal to s minus 1 by s plus 1. So this is a relation between reflection coefficient and standing wave ratio. Okay, thank you.
Like, share and subscribe. Hit the bell icon for more updates.